All right, guys, let's start over. So, hello and thank you for coming by. My name is Ibon Tolosana. I'm CTO at Ludei. A little bit about Ludei I would like to share with you guys is that at Ludei we try to fill in a gap, which is actually an industry-wide gap. We are focusing on making HTML5 work in every circumstance. So we are strong into making HTML5 gaming work. Oh, sorry, I'm gonna just make caffeine. Yeah, right. We also are able to bring in solutions for enterprise-wide HTML5, and in essence, what we have is a cloud compiler and some technology stack that maybe you could give it a try and see how it's working. On our daily basis, we are very seriously into graphics and WebGL and everything gaming related. And this presentation is a little bit about how to make 3D content, specifically how to use WebGL for 2D games. Because you will see that the paradigm of making 3D for the flat side of the 3D, which is 2D, is not that straightforward in the end. So the first question I've got is the browser as a gaming platform. And it is not that long since probably we realized that a browser was kind of a toy thing. JavaScript itself was a language which was devoted to probably make some forms validation and nothing else. But right now, the browser, as we know it, is a complete execution platform. It offers us a plugin-less environment. It is fast, extremely fast, I would say, and it's getting faster every day. It is quite reliable, and offers us a very compelling language, which is JavaScript. Dynamic languages are, specifically suited for many different applications, and I would say that especially for gaming. And the web, as we know it, is actually the only platform which is here to stay forever. We have seen many other big platforms that have failed, merged, or disappeared, and we can think about some others like Nokia, or these guys at BlackBerry, or these guys at Palm OS. All of those have disappeared, but the web itself, is not only here to stay, it is evolving and is doing that very rapidly. So my point is, yeah, give me my precious, I want to believe in that the web, as it is going to be evolving and it's going to be offering us lots of new solutions. Right now it is not overhyped, not anymore. We are completely realistic about the possibilities or the things we can achieve by using not only WebGL, but all the HTML5 ecosystem of solutions. And the other thing is that we have some facts in place which are shaping up the gaming ecosystem in the web browser and HTML5. So the first fact is performance. And this is something that no one can tell us, can't tell, in the contrary. JavaScript is probably the fastest evolving virtual machine around. The performance is being leveraged at least 10–20%, being based on our own measures every 6 weeks, in which we have a version of the major browsers around. And there was a milestone in 2010 in which Google introduced in the V8 system the crankshaft, or however that's pronounced. For a Spanish guy like me, this is like, well, huge endeavor to say. I would try only once. Crankshaft. Sounds good? Okay, cool. So that simply introduced 100% performance suddenly on the fly, because it's JIT in the code to native. The Octane, which is a performance measure, performance benchmark, you see that from 2011 to 2013, the difference is probably 5x. Then we have ASM.js around, and I think that many of you are already into HTML5 and JavaScript gaming development. Honestly, I will never write code like ASM.js requires that to be compelling, and high performant, but anyway, it is there. And then the other day I read something about, these guys at WebKit. They introduced a fourth layer of JITing, which is called the FTL JIT. This is honestly, something outstanding, and it's beyond my understanding. But in the end, what you do is JIT compile to LLVM level. So it's going to be introducing a new level of performance, probably doubling the performance that actually it is offering us. What is the bad news is that these guys are Apple, at Endogamic, and the solutions they build up are just for themselves. So we won't be able, from, for example, a QQJS standpoint, we won't be able to benefit from this kind of cheating. But anyway, the desktops will, hopefully. The other set of facts is that we have very compelling features for gaming right now. We have web audio, we have web workers, shared web workers, which allow us to have parallel execution in the browser, kinda. Then we have pointer logs, we have local storage, or several different strategies for app caching or keeping our content locally. We have WebSockets or WebGL, full screen, whatever, but we must be realistic about because this is the desktop. What's going on in the mobile ecosystem, honestly, from our standpoint, and as a company, we have already delivered 2,000 games, 2,000 titles to the stores, people around the world using our technology. We see that the thing is not, as we expected. There are not only missing features across different platforms, it is a matter of performance, fragmentation. There are blacklisted GPUs. iOS is hurting the HTML5 experience, with every version that is releasing or, put in the market. But anyway, that's something we must deal with. But on the other hand, I can see, how Internet Explorer 8.1, and Chrome, how they are catching up and how they are being evolving. And the only thing I can think of, is that this is so rapidly changing and it's evolving so fast that in the end, it's quite beautiful. The web itself is, in the mobile space, it's going to succeed, and I'm pretty sure about that. So guys, whoever is into gaming knows that a game is not the rules, and the game is not only the graphics. A game is built out of several different modules, things that are interrelated. There are physics, there's input, there are networks, artificial intelligence, sound, animation loops, whatever. But then we have the rendering stage. Until pretty recently, the rendering was probably the worst performing part in our gaming. But now we have WebGL, and we also have hardware accelerated canvases and stuff like that. So that means that suddenly graphics are not going to be the bottleneck of our games. And all the time that we are not spending in fixing the graphics or making the graphics run faster is time that our processors could devote to working all the other parts. So it's a situation in which we only will be seeing, better content and how the bar of the quality is going to be risen with time, because the graphics, suddenly disappear from the equation of the slow things. So from our perspective, in these 2,000 games, what is the current landscape for the games? It's that they are either low to mid-core games, not very demanding in graphics, sometimes require hardware acceleration, most of them don't. They are focusing on low-end GPUs. There's fragmented encoded, they are slow, and this could be something like, okay, everything is bad news, but in the end, it's not only that I'm optimistic, it's that this is how I feel about HTML5 gaming. It's something like it is evolving, and guys, it is going to be succeed. We have in the audience, there are the Pixie guys. These guys are making probably the best renderer available for gaming. And what's going on there? I can see that probably they are being published with our platform 50 games using the Pixie. So everything is getting better as the cost of nothing. So for us, when we go to develop a game and do something with WebGL for 2D, we have to make some development decisions. And I will enter into code and optimizations, in a couple of slides, but it's important to notice that what is WebGL actually? WebGL is an extremely low-level API. It is not something that you could say, okay, let's use WebGL and our problems are going to be solved. There's no Canvas API. That means that you don't have any of the expected higher-level drawing primitives and APIs available for you. Suddenly, you won't have even a single field text or field path or draw image or stuff like that. You will have to rebuild everything from scratch. That's why it's interesting that we have the Pixie and stuff like that around, because they will, do all that geometry and dirty things on our behalf. it will work in an immediate or in retained mode. The canvas is working all the time in an immediate mode. Wherever you are, wherever the primitive you are going to be doing is going to be pushed to the screen. That is extremely bad, as we will see right now with some examples for WebGL. Because for WebGL, what you have to do is talk the less to your OpenGL driver. The less you talk to it, the better, because you will save tons of time. And then WebGL is always present in a place where there already exists a hardware-accelerated canvas. So it sounds like, why would I choose WebGL for 2D gaming? What is the point on it? So then there are the good things. First thing is that you will get a superior performance. And by superior, I'm talking about 10x, 6x, I don't mind. Extremely powerful thing. So you will be able to devote most of your computation code into all the other parts of your games. You will get unparalleled visuals. Something good that OpenGL and WebGL offers you is the possibility to customize and build your own shaders. You will be able to overcome a not so gaming-oriented API. And this is something that whenever or whoever was the guy behind the Canvas API, he didn't have in mind gaming. Of course he didn't. I think that probably he was thinking on, okay, let's build some fancy graphics on the fly and put them in a canvas, and that's all. But the API is not very animation friendly. Then with WebGL, you will be able to have things like tinting. Tinting is the process in which you are able to tint your texture or geometry, whatever, using the vertices and painting the vertices without the hassle of drawing your image to an off-screen image, grabbing the pixels, modifying, uploading the pixels, building a new image. You will be able to do this on the fly at zero cost, more or less. And best of all is that the 3D model gets extremely simplified with 2D. So all these things related to culling or depth testing or the lightings or dealing with normals or stuff like that will be completely out of the equation. You will be able to focus only in bringing fast graphics to the screen and extremely well-looking graphics. And then, as I told you before, there are plenty of frameworks to help with these things. So how could we do that? It is not the way, but it's a very good way to do this thing. By the way, have you seen this Adventure Time series? I love that thing. It's like, yeah, I would like to be the dog. Yeah, slinging monster is not as fancy as bending yourself and yeah. Well, anyway, moving the wave like that. Well, anyway, getting back to real life, I would like to welcome you to the assembler of the web. That is what basically WebGL is. It is a mashup of C-like function calls, and you will love this thing pretty quickly. But first, and before this, I would like to show you just a bit of background of what's going on behind the scenes with WebGL. What happens with Canvas, or what happens with a WebGL-enabled Canvas. And then is that forget about your paradigm, right? Is that correctly said? Paradigm? Okay. Who's making the count of wrongly pronounced words? It's just, I think I will outperform you guys. So yeah, maybe we can try later. I would like to speak in Spanish with any of you, so I can get something in exchange. Paradigmed, correct. So first of all, what we need to do is make a mindset change completely. One, when we draw things on a canvas and when we are drawing things with this very high-level API, the lowest thing we have in mind is just a pixel. And in WebGL, pixels suddenly vanished until probably the end of this graphics pipeline stage. So until you get to the output merging, your pixels don't exist because what you have is geometry. So from now on, whenever we are going to be thinking on a sprite, what we should be thinking of is two triangles. Okay, that's easy peasy. I'm able to do that myself. So, and that's dreaming of being a yellow dog. So it's not that much. So no more high-level primitives. And what is the point is that why is this so powerful is because there are two parts which are programmable, which are this thing, the vertex processor and then we have the fragment or the pixel processor. That's fine. So from now on, our best friend is going to be the WebGL program shader, which is these two parts. So vertex shaders are going to be dealing with geometry and are oriented to your scene geometry. And then we have the fragments, which operate at the pixel level. And the things that we've seen before, these elements are one stage feeds the next one. In OpenGLES 2.0, which is quite simple, we only have these two programmable parts. In OpenGLES 3.0, we have some more, and in 4 we have extremely much more. So the point is, WebGL is going to be no more. It is completely primitive oriented. I mean, WebGL only understands of triangles or fans or quads or lines, or maybe not. Have you seen this shader toy thing? Has anyone seen the shader toy? Only you guys? Okay, so you will love this thing because this is impressive. We all think that WebGL is going to be oriented to triangles and stuff like that, but then there are these crazy guys at the shader toy in which they say, okay, I'm going to be taking only 2 triangles and I'm going to be drawing all the content procedurally, and they are able to deliver, this. Oh man, there's no internet connection. Another fail. Who's taking the count? I'm sorry. No. Oh, it was so fun. Maybe I could. Okay, let me try that then. Okay, all the other examples are locally stored in my laptop, so. Oh man, that was very funny because in the end, I will try to make a rough description of this thing. One is a fractal, and it's a wavy fractal, which is resembling something like an imaginary world, which is built out of these cartoonish colors. So in just 2 triangles, you could build, a complete universe. And it's so rich and so beautiful that I would like to save like 2 minutes at the end of the presentation to try to show you guys this thing. So okay, getting back to the program shader. They run on the GPU, and this is the good news. The GPU is extremely well performant. So your CPU could be doing something else while your GPU is pushing content to the screen. And that's why WebGL is so fast, but we should do it the right way. Apart from that, it's written in GLSL. And this is quite funny, and this is why this is probably the assembler of the web, because yes, GLSL is a kind of C-like API in which you deal with very low-level things. And then how we interact with these program shaders is between these 2 elements, the attributes and uniforms. I wouldn't be talking about this thing unless by the fact that the uniforms are the things that could completely ruin our performance in the system. So from now on, we are into WebGL code. And the most important thing is how we start to put content on the screen. The first thing we have to do is set up a projection. And this welcomes you to the flat side of the 3D. Because from now on, we're going to be using 3D to show you flat content. You could do this in 2 different flavors. One is setting up an orthographic projection, which is the left one. A graphics library expects, at least OpenGLES expects, that all your geometry is going to be mapped into a cuboid. So that is one way of doing it. The other one is you can set up a projection matrix, and you can set up a 45 degrees in a field of view, which is vertically measured. So what you're going to do is fake a camera and position a camera at half the distance of the height of the screen. Do you know that? This is something like that. I know. What are you talking about, man? Show me the code, and that's the thing, because you will do this only once in your life and forget about that. Set up a projection matrix or an orthographic projection, and then set up a viewport, and then you are done. You can start pushing content to the screen. I know that until now this has been like, man, what are you gonna be showing? You were talking about, WebGL 3D for 2D and stuff like that. Okay, let's go for it. So now, what is the best thing we have to do? How are we going to be making our WebGL be extremely performant? The key concept is that one. It is the batching things. So a batch. I remember when I was young and I studied computer science, they told us that a batch was something that happened in a host. And that was, all the jobs were going to be executed in a sequence and stuff like that. This is pretty much the same thing. What you want to do by batching geometry is not push the content to the screen until it is extremely necessary, or more than extremely necessary, until it is necessary. Don't do that. If you can, avoid it. So what is the condition by which I should be in need of pushing the content I have already batched to the screen? It is because I must change any of my uniforms things. Think of uniforms as if they were a global variable for one of those shaders. So a uniform, for example, is set up for which image I'm going to be drawing content to the screen, or a uniform is something that allows me to project the element on the screen. So for example, if I have a 3D model of this chair, how I put that on space is something that is ruled by a matrix, and that matrix is uploaded as a uniform. And the other thing is that if I'm using color for drawing things and suddenly I'm going to change that and use a texture or something different, I must change my program shader, and that is also a source of batching things. So what's the point? In 3D, what we have is a static geometry. We have a model for a chair, we have a model for a monitor, we have a model for this room, we have a model for whatever. But in 2D graphics, we have complete dynamic geometry. Every frame, my sprites are going to be moving to somewhere else, and in an unpredictable way. I'm unable to know programmatically or to produce procedurally something to position my sprites on the screen. So I have to calculate all of these things. And think about it, about this. On an average game, I probably can have like 1,000 sprites on the screen. And for the graphics library, there's no difference between our sprite, which is just 2 triangles, or a model of this chair, which is going to be like 50K triangles. For the GPU, there's no difference. But if I want to draw this chair 10 times on the screen, rotate it in different angles, what I have to do is set up and modify the uniform, which says, okay, modify this thing, and then push the content to the screen. If I want to do this 1,000 times, my performance will sink. It simply won't be there. So what I have to do, and this is very important, is since everything is going to be dynamic geometry, what I need to do is make client-side calculations and client-side transformations of my geometry. So the point is try to transform wisely. For example, in our graphics libraries, what we have is several different ways of calculating a transformation matrix for something. If it is only translated, we only move the positions. If it is rotated, we just rotate. If it is translated and rotate, so there are different ways. And in JavaScript, this is very important because JavaScript is extremely sensitive to the quality of your code and to the time and to the amount of instructions you're going to be doing. So if you do this thing correctly, I'm going to show you, okay, yeah, some code. This is a very good marketing test of some batched content. How many of you know about this bunny mark thing? Okay, plenty, right. Cool, so for the other guys who don't, only you and me probably. This is let's say, best example of the best conditions for batching content on the screen. We only have one sprite, which is the bunny. It has tinted vertices, okay? And then we only have one image, and I will be able to batch everything on the screen, and then probably batch 16,000 of those elements to the screen. So how many frames per second would you expect for anything like that, in a MacBook Air, which has a toys, graphics card? I don't know, but batching is this thing. So you could start adding content. Okay, there are like 15,000. What about 15,000? We are still running at 60 frames per second. What about 22,600? What are we running at? 49. That was completely unexpected. It should be like 60 still. But anyway, this is the thing, if you batch wisely, you will be able to push tons of content to the screen. And the thing is that they are moving, they are jumping. What is the bottleneck actually in this demo we are showing right now? It is not the JavaScript. JavaScript is extremely fast. It is able to make calculations for, and I will show you some code of this thing. It is able to make the calculations for, you don't see this, right? Do you? Where are you, darling? There. Well, after all, I wanted to be a dog, you know, so calling darling to my laptop is quite normal. So we are moving the bunnies with this thing, and then we have a loop over here in which we are adding the missing elements, and then we have a graphics library which is treating each sprite as a complete actor, which has several different properties like position, rotation, escalation, parent-client relationship. In fact, all of the elements are inside another element, which is a scene, and so on and so on. So what is the bottleneck for this thing? It is not the JavaScript. It is actually the graphics library. It is actually the graphics pipeline, sorry. We are putting so much content to the screen that the GPU simply is unable to move more content from video memory to the screen. That's why the frame rate drops. It's not because I could seriously continue adding more elements to the screen. So if instead of using bunnies like this size, I was using 2-pixel images, I could push probably 50,000 elements to the screen. So this is the first, consequence of batching content. Okay, sounds good. And I think it is quite compelling already. But then, what if we do it the wrong way, man? This is very likely to happen. So you have been working in your WebGL implementation for a week, and then you have several different images in place and stuff, and then you forget about batching appropriately. So the launch of your graphics library is a pain in the ass, literally. I love this picture. I could continue looking at that in a loop for an hour. So probably this was recorded somewhere in Spain. I'm sorry. So okay, batching in general is that thing. Okay, batch all the content you can, and then push all the content at once at the same time to the screen. Honestly, the previous example was just a marketing-like thing. Never happens in reality. So don't pay too much attention to how many elements you can push to the screen with the same texture under these ideal conditions. Never happens. But what you have to do actually is batch appropriately and batch wisely. So sorting on the shader program and on the geometry is probably the most intelligent thing you could do to batch content to the screen. And why is this thing? This is probably the foundation of every modern rendering engine. No matter whether it is 2D or 3D, it doesn't matter. If you don't do this appropriately, you will get into a situation like the one we are about to see. We are going to be doing so many program changes that the CPU will stall, and we'll see that with only 500 elements, our WebGL performance has simply vanished. So it's pretty much like this guy, that's my WebGL. Oh no, it's a crap. So that's it. Here we have just 500 elements, 250 colored quads, 250 textures on the right side. But we are doing this so wrongly that the performance is no more than 15 frames per second. And that is why, because we are not batching appropriately, we are sending a color quad, and then we are changing the program to draw one sprite, and then one quad, and then one sprite. And this is where this performance is being lost. So you must try to sort the content using, for this shader, try to push as much content as possible to the screen. Of course, this is a two-dimensional engine, and sometimes the order in which our sprites are being drawn to the screen comes from the engine itself. But then the problem is not in the engine. It's not in the graphics library. The problem is in the logic behind our game engine. So we should revisit that thing. Okay, Now we have another thing which is pretty common. Whoever is into HTML5 gaming and is using the canvas, they probably don't pay too much attention about texture packing things. So from now on, every of you will texture pack everything, period, no questions. Even you. So the reason is pretty much the same one as before. Instead of changing from two different shader programs, we will be forced to flash. Don't count this one, okay? I said that correctly. We'll be forced to flash the content because we are changing between one image and the other, okay? So this is the result with 500 sprites again. And in this case, we have 27 frames per second. The difference is that we are only flashing the content. We are not switching to another vertex or shader program at all. But the performance is a crap. So why should you texture pack everything because of this thing? If you texture pack, you won't be in need of changing from one texture to the other. And your system will be able to push all the content at once, pretty much like in the marketing demo we did before. We could change that on the fly if you wanted to, but honestly, I think time is going so fast that we should move forward. But how will we tackle this thing? How will we get with a nice solution for this kind of behavior? If we texture pack everything and instead of having two different textures, we have only one, the content will be batched at once. And we will be benefiting again from the 60 frames per second for 20,000 elements on the screen without, too much of a problem. So what is the thing, Actually, there's another thing which is for 2D games and is the following. This is a pro tip. I love pro tips, which is the fastest pixel you have on the screen is the one you are not drawing. I know I'm so smart, sometimes. But take this seriously. If you can, how you say that, if you can't cull, C-U-L-L? Cull? Okay, take that one. Sorry. If you can cull the content before pushing the content to the screen, so instead of letting the system do the clipping for you, if you are smart enough and make the clipping before, you will be saving tons of system, tons of processor time again. And another thing is, don't think that because I have an image and I have a huge, empty space around, since I can't see it, it's not taking time. So this is something for, designers and people like that who love using almost transparent shadows for everything. All those pixels take time as well. And so in the end, you will be hitting a huge problem, which is you are moving more content than expected between video memory and the screen, and that stalls the GPU as well. Another thing we have for WebGL is that of compositing. That is so fancy to have your WebGL composited with the underlying document in the browser. It is so cool and so cute that you probably don't want to do that never on the mobile space. Because when you make a composition between your WebGL and the document, what you are doing in the end is redraw everything on top of the document without taking into account, for example, blending modes and stuff like that. If you have done, some of you have done some WebGL content and suddenly you see that, okay, why is my WebGL getting reddish or bluish, or why is it tinted with some other color? It is because the browser makes a composition between the canvas, which can have an attribute with color, and the document, and suddenly you are not seeing the expected result. Apart from that, compositing is very expensive. It takes a lot of time to do. So if you can avoid doing that, whenever you build your canvas context, you can pass it in, an extra object. You could tell the system to, okay, use alpha as false and not composite the content with the browser itself. This is probably the behavior you will expect, because our games, on average, all of the games have, a background image or something that is taking over the whole screen. So in the end, this is just wasting time. Another thing is the anti-alias thing. Anti-alias, right? Anti-alias. Anti-alias as well is very expensive because it's a full screen filter that must be done. And how does the browser do anti-alias? Either super samples the canvas. I mean, if you have a canvas of 800 by 600 pixels, the browser behind the scenes is going to be having a 1600 by 1200 pixel, and then it's going to be reducing that. So the anti-alias is automatic. So that means that you are, taking longer than expected. Or it could make a filter. So it could draw everything to an off screen and then use that off screen as a source for texture, and then push that content to the screen with a shader which is filtering the content, which in the end is a huge performance. The difference is exactly this one. This is 15 sprites, small sprites rotated and translated with tint and color vertices using anti-alias true. And I can't see anything, do you? Okay. Okay. That was a joke. My browser is trolling me. So we get like 23 frames per second, no more than that. 20, okay, don't do that. 18, 20 frames per second. And you see that if you make a zoom to it, you see that the sprites are so crispy and so beautiful and so forget about me, man, because what I want this thing is to run at a steady 60 frames per second. So the result and the difference is exactly this line of code. Whenever you ask for the context, say anti-alias false, and this will be the result. So we get our expected 59 frames per second, and there's only one single difference. No one in this room is able to spot the difference between the anti-alias version and the non-anti-alias version. Or maybe you can, I don't know. But this is the thing. And apart from drawing the sprite to the screen and applying a random tinting to the vertices, just for the add up some spice to the equation. So one single line of code, a huge performance, and that's because of the filtering for the anti-alias thing. So when I was thinking about this example, I was like, what does this likely thing reminds me of? Is this the same thing? Oh, honestly, I was like mesmerized seeing that everybody loves the Hypnotoad, don't you? I do. And then we came to the point of focusing specifically on the mobile GPUs. Mobile GPUs are even a worse environment for WebGL, mostly because they are very constrained by bandwidth. And we've seen that bandwidth is something that we have already hit the limit with the marketingist demo we've seen before. That was on a desktop, so think about that happening in the mobile space. It will happen even faster than expected. The other thing is that the mobile GPUs are tiled, so the system doesn't take primitives that span across the whole screen, so they do that on tiles. So it takes even longer to draw your primitives to the screen. And then on average, mobile units have a small amount of vector units to draw the things to the screen. And then we have the NVIDIA K1, which has 192 CUDA cores, and it's like pretty much like hardware porn. So we don't have to worry about this thing anymore if we are into a Tegra in a K1. But I haven't seen devices around yet in the mass market with this kind of technology. So we have to do something in the end. And one thing we can do is MIP mapping the content. MIP mapping is something that will this image at the bottom is a MIP mapped version of the original image. So what the MIP map does is build different versions of the same image for different resolution spaces when applying the image. I will explain that. So for example, in the previous example in which we had the 32 by 32 pixel element sprites, what happens if we want to draw a 2000 pixels by 2000 pixel image in a 32 by 32? The thing is that the GPU has to go through all the 2000 by 2000 pixels, sampling and picking the content to put in there. That is a lot of bandwidth which has been, wasted. So mip-map allows us to, okay, you have a 2000 by 2000, and then you have a 1000 by 1, and a 500, and a 250, and probably a 32 by 32 version of it. So the system will balance and will select exactly which is the best image resolution for the expected size of the sprite. The only drawback with this thing is that there's a balance between the memory, because the image will take much memory than expected, and the visual quality, because the lower resolution version won't see on the screen as crispier as expected. And then another thing is that your pixel art could be, a little bit hearted with this thing. Are you guys, any of you, into building games seriously? I mean, professionally, or you are? Okay, then it's a higher level, mission or something. You are? Only you? Is anyone else? Okay, guys. We have plenty of people around. Cool. I'm running out of time, so it was my plan to open my WebStorm, and start coding in there and show you why this thing is there, but, let's make a leap of faith, and believe me, this happens. Or maybe we can, catch up later, and I will show you exactly how it works and why is this thing. Then we have another thing, which is the buffer data and buffer subdata. We are in an environment in which we have said previously that we have completely dynamic geometry. That means that the process by which I build a model and I upload that model to the video memory and it's there forever is not true. So what we have to do is build frame after frame. What we have to do is build all the geometry on the fly. So that means that somehow we must upload all that geometry to the video memory, because we are making the calculations in the client, in the JavaScript itself. And honestly, we have already seen that dealing with 25,000 sprites on the screen is not a problem at all. So JavaScript is more than capable of bringing this kind of performance. But what we have to do is upload all that content to the graphics library, to the graphics pipeline, I'm sorry. So that's done using an operation which is called buffer subdata. So you define a buffer, you define a content, you upload the content, and then you say, okay, upload or update this content with this new content. That's why 2D in 3D is the worst scenario, because the geometry is completely dynamic. But what happens with buffer data, we have two versions, and buffer data is way faster than buffer subdata, and that is something that happens behind the scenes for you. The GPU is going to be blocking operations in a buffer until it has uploaded all the geometry to it. So if we are in this situation in which we have complete dynamic data, what we have to do is use buffer data instead of subdata where possible. The other thing is that there's no point in, okay, since I have realized that I have a batch for 20,000 sprites and now I will be in need of 40,000 sprites, I will be building a twice the size buffer, and that's all. Actually, it doesn't work that way. There's a limitation in the number of elements you can push with one single draw element call. And then mobile GPUs on average don't behave appropriately if you define a buffer for, I don't know, 256 megabytes or stuff like that. So you should be, down to earth and realize that probably 8 to 16K triangles are going to be more than enough. So if you want to not stall your GPU, stick to these things. Buffer data is always better than subdata. The other thing that happens is filtering, and filtering is like the anti-alias thing, is something that we want to apply to the whole screen. This is probably a very compelling reason to come to WebGL, because we can filter the whole scene with something else. We can change colors or make it wobble, or I don't know, apply a spiral on top of that, or whatever is there. But the thing is that since a mobile GPU is extremely constrained by bandwidth, probably we would like to take filtering, seriously as it is, and probably not applying more than one filter on top of the other, because performance will drop abruptly. It is very intensive. It also needs a frame buffer and a stencil buffer for itself and stuff like that. But a fun thing is that you don't have to apply a filter to the whole screen. You can apply a filter to a region in which, for example, you have a warping area in which the sprite does a wobble like blob, so you don't have to apply it for the complete scene. So I'd like to show you an example of a filter, a very fast one. If you want to see a very good examples of filters, go to the Pixie engine. They have plenty of filters in there, and then you will enjoy it. So this is a filter. So what we do originally is draw a scene, which is the guys moving in the background, and then the turbulence, which is the black thing, and the coloring thing, which is a plasma, and all the school plasma shader. These two are custom shaders. But then with the result, we are feeding the result into a filter, which is making this wobble, this wobbly thing. And it could be very easy to add another filter on top of that, like, on a spiral, and then you will be a slave for the hypnotoad forever or something. But then how many filters I could apply one on top of the other is unlimited. Being said that, I will be pinpointing between the frame buffer and the screen all the time, so I won't use more memory than expected. But the thing is that this in a mobile GPU, in my Nexus 7, this works great, 60 frames per second, no problem, but there are other devices which are not that capable. So we should pay special attention about, what my mobile GPU it's going to be able to handle. The thing is that why is this taking longer? Why it won't perform is because it is using tons of bandwidth. It is moving 2 times the whole screen between one filter, feeding that to the other filter, and then feeding it back to the screen. And so on forever until you want to. Okay. So what is the fun fact is that in my desktop, I can add any of those effects at 0 cost, because the GPU is so fast at doing this that it will, allow me to devote all my time to all the other parts of my game, as we said before. And then there's one final thing for the GPUs, which is precision and branching. Whenever we define a shader, there is an implicit precision for medium precision, or high precision, or low precision. If we expect our content to go to a mobile device, medium precision is your precision, actually. High precision will hurt performance a lot, and low precision will bring to the screen, very low quality in graphics. So always try to stick to the medium precision unless it's strictly necessary. And then the other thing is branching. If you branch inside a shader, unless it is I won't be able to pronounce this, I'm sorry. Unless it is branching, your performance will be harder a lot. So for example, we have a Canvas API for WebGL, which is a complete one, and the pattern shader is divided into 4 different shaders, one for repeat, with X, Y, and no repeat, because otherwise the performance, simply drops extremely abruptly. I'm talking about that your frame rate goes down like 10 frames per second or stuff like that. And up to this point, I know this is kind of, why do you tell me this thing, why don't I use the Pixie thing, and that's all. And that's my recommendation, actually. Dealing with all this stuff is fun. I recognize that, but probably it's not, production ready for the mass market. Then there are other things like vector geometry. How do we draw vector geometry? Because it is not available in the WebGL in itself. So we can do something like that, and this is actual geometry in the system. So we have a shape which is composed of 100 paths for each of those lines on the screen, but then we are sorting the geometry. We are simply changing the transformation, and we are batching the system. So despite what it may seem, every 10 of these elements have the same rotation angle. So I'm batching 10, pushing 10, changing the transformation, batching 10, randomly position them, pushing another 10, and that's why I'm able to get, these 58 frames per second, because otherwise we will have on the screen probably something like 200k triangles, 200,000 triangles on the screen. So it doesn't seem like this works even in the mobile system, works pretty well. And then we have some examples of Canvas Path API. This is an example of our Canvas API for WebGL. One of those is WebGL, the other one is Canvas. And which one do you think it is, actually? Which one? Maybe this way? Okay, the non-anti-alias one is always WebGL. we said before, that non-anti-alias content is going to be way better for the performance, and actually it is. And what about text? This is something beyond my understanding and my scope, but if you want to go and have text in your WebGL-based games, either guys use sprite fonts and treat them as draw image primitives, sprites in the end, or draw your text in a canvas, upload that to the GPU, and treat that as a temporary texture, which could be reused, across your game. I know, but what can I tell you about this thing? So, guys, another thing about WebGL. This is all WebGL related. Fast graphics, batching, primitives, intelligent way of sorting things for shader and geometry and stuff like that. These are general rules too. But then we also could break our content because we write very bad JavaScript code. And this is something to take into account. One thing is, request animation frame, don't make your own time measures. Use the parameter that comes into the request animation frame function because it has nanosecond resolution. And also make the following, quantify the time that takes your drawing time and quantify the time that takes the request animation frame. Request animation frame should be steadily reporting 66.66 milliseconds, steadily, without any variation. And then you will realize that probably your drawing time is taking 2 milliseconds. So what is the browser doing for the rest of the 14 milliseconds? It's doing nothing, and that is the great thing. You are running at a steady 60 frames per second, and your browser is doing nothing. And that would probably be in part because you are batching appropriately the content. So you could devote more milliseconds to all the other parts of your game. A more intensive artificial intelligence, a more intensive, network subsystem, whatever, will work. So then we have loops, and I know we all have been attending and looking around tons of micro benchmarks about this loop is faster than the other, Chrome is taking longer to traverse an array than Firefox. Do you know that? Micro benchmarks lied at you. That's it. It takes some time for the JIT system to identify the hotspots of the code and translate that code into actual native code. So if you want to micro benchmark things in loops, my advice is don't do it. Right now, the V8 implementation, the ASM.js implementation, JavaScript core implementation, all of them have complete units devoted to optimizing your loops. So don't pay attention to that. Don't write code like that in which you have, okay, or I'm going to be making my loops, inversely. I'm going to go into the end, to the beginning, because the comparison with 0 and in assembler, is just a jump if 0 or whatever. It's not worth it at all. The JIT will do that for you, and way better than you expect. The thing is that the JavaScript virtual machine is evolving so rapidly that next month there will be some crazy guy in Russia who is going to be, fine-tuning the virtual machine here and there, and suddenly you will get 300% extra performance if you did correct JavaScript code. And correct JavaScript code is writing a loop as it is expected to be. And then suddenly, why is this thing going slower than before? Because you did a hack or a trick or something that you weren't supposed to be doing there. Another thing is how JIT and JavaScript work, and this is quite important. It was a time not so long ago in which we were told that, okay, all your object properties and all your object functions should be in the prototype. Now that is not the thing. If you see any presentation of a modern JavaScript engine, you should inject every attribute of your class in the constructor function. And that is something, and that is, that statement is because of one thing. Every JIT compilation, every JIT thing, everything that has been JITed for a certain class, before time you are making a construction for a new object. If during the construction stage, the virtual machine identifies that this object corresponds to a previously known object, this object out of the box will benefit from all the JITed strategy that has been already done for it. So inject that in the constructor. Don't defer that to the prototypes. And then this is another thing, which is the inline caching. If you keep your functions small, the system will inline them pretty much like in C++. Things that you shouldn't do in your code, at least in sensitive parts of the code, which are parts of loops or parts of important or let's say performance-sensitive parts of your code, don't use for in, because that will bail out the function from, that won't even be JITed, the function. But then try catch as well, big code functions. Try not to allocate in your loops. That's something, as smart as the fastest pixels is the non-drawn one. Try to avoid these WebGL synchronous functions. And what happens when all these things fails, when you have done correct batching, you have written correct JavaScript, I don't know, maybe you're going to have a, like this guy, which was trouble, how do you say that, a rocket? Yeah, but then what you have to do is you have such a intensive game, such a big one, that the size of the viewport you defined, is simply too much. You have too many elements on the screen. So either you reduce the size and then upscale on CSS, or you simply get rid of some complexity of your game. And that's pretty much all, guys. I've taken 56 minutes of your life. I'm sorry. Sorry? I can put the slides online, yes? Okay, thank you, guys.